Alright, so Newton's third law tells us that every action force is going to have an equal and opposite reaction force. So when Miss Cunningham kicks the wall with a force of 700 newtons, that means that the wall is going to kick her back with a force of 700 newtons just in the opposite direction. So that would be a force of negative 700. The difference between an elastic collision versus an inelastic. Elastic is when they both bounce off one another, so that would look something like this. And inelastic is when they stick together, so something like this. Once they collide, they are now stuck together and they go off at the same velocity. Force of friction. So force of friction is found by mu Fn. So the two things the force of friction depends on is mu, which is the coefficient of friction, and the normal force. And the normal force. So normal force is how much the surface is pushing back. So how much the surface pushes back. So we've done enough examples that you should know that your normal force is almost always equal to your weight. So if I have a heavier object sitting on the table, that means the table needs to push up with a greater force to balance out. The two different types of frictions, we've got static and kinetic, and what do we know about them? So static is when the object is not moving or while it is still at rest, and kinetic is while it is moving. Kinetic is always going to be a little bit less than the static. It's harder to get it moving. Once it's moving, it's a little bit easier to keep it moving. We've got two discs, magnets, whatever, I don't know, unequal mass, 1.5 and 1. They are in a frictionless horizontal surface. When the string is cut, they move apart. Newton's third law tells me that the force between them are equal but opposite, right? So this guy feels a force to the left, this guy feels a force to the right, but it is the same force, right? Same magnitude of force, just opposite directions. Which magnet experiences a greater acceleration? So think about it. They have the same force, and F equals ma. Just because if they have the same force does not mean they have same acceleration. In fact, if they have the same force but they have a smaller mass, that would mean a more acceleration. So 1 kilogram will have a greater acceleration. The one that will have move off with a greater velocity will also be the 1 kilogram because, again, it has that smaller mass. You can think about that in terms of the acceleration, right? More acceleration will go off with a faster velocity. Or you can think about it in terms of the momentum, which I'll explain once I've answered this. The greater momentum, so think about, these both are at rest, which means you have a total momentum of 0. So the only reason, or the only way these two can both have a momentum of 0 in the end is if their momentums cancel out. So they would have equal momentums, just in opposite directions, which means that the smaller mass would have to have a faster velocity. If this was the 1 and this is the 1.5, this one would have to go a little bit faster than this one for them to still have equal momentums that cancel out. And then greater impulse, so you can think about it as F delta T. This side of the equation, you've got the same force for the same period of time, or you can think about the other side, the M delta V, the change in momentum. We just said they go off with equal momentum, so they have equal change in momentums, which means they have equal impulses. What happens to the momentum of an object as it falls? So think about as it's falling. Well, momentum is m times v. The mass obviously isn't changing as it falls. Your velocity is. As you get faster, your velocity is increasing. So if your velocity is increasing, keeping the same mass, that means your momentum must be increasing. Between what two materials would need the greatest force to start the object moving? So think about it. The reason you need a force, like a bigger or smaller force to start an object moving is because they have different static frictions. So to start it moving, that's before it's moving, so rest, static. The one that needs the greatest force is just the one that has the greatest coefficient of friction. It's harder to start it moving. The greatest coefficient of static friction would be the rubber on concrete. So that is the two materials that you would need the greatest force to start the object moving. And which one would you need the smallest to keep it going at a constant velocity? So that tells me I'm going to be looking at these kinetic coefficients. And now I'm looking for the smallest force needed. Well, that's the smallest friction force, which would be ice on ice. Here we've got a graph of friction force as a function of the applied force. What type of friction does the object experience when the applied force is 10? So applied force of 10, let's look. This section of the graph is going to be the static friction before it starts moving. I push with 10, it pushes back with 10. I push with 30, it pushes back with, 20, it pushes back with 20. I push with 25, that is where it changes into the kinetic. So this part is going to be static, right? That's before it is changed to kinetic, before it starts moving. And what that means about the motion is that the object is at rest, or you could say not moving yet. B, what is the applied force when the type of friction changes? Well, it's static here, it's kinetic here, that means it's changing in here, and it changed at an applied force of 25 newtons. What is the applied force needed to make it move? So if I push it with 24 newtons, it's static, it does not move. If I push it with 26 newtons, now I'm in the kinetic, it does move. If I push it at 25, that's what's needed to start it moving. So that I'm going to call my maximum static friction. That is the friction force that I need to overcome before it starts moving. What is the coefficient of static friction? So looking for mu, I'm going to use my FF equals mu Fn. First, I need to find the normal force. This is a mass of 3, so I can find my force of gravity is just mass times 9.8. So 3 times 9.8 is 29.4. That means my normal force would also be 29.4 because it's balanced up and down. So mu, I'm looking for, Fn is 29.4. If we're talking about trying to find the coefficient of static friction, I should use the static friction force. The maximum static friction force is the 25, what we just said. So I'm going to plug this in. And then we're going to divide over, and that gives you a mu of, actually, I don't know. Let's try. 0.85. Now I'm asking again for coefficient of friction, but now I'm looking at kinetic friction. So whether it's moving or not, the normal force hasn't changed. Still looking for mu, still using the same normal force, but now I'm looking at coefficient of kinetic friction. So that means I use the kinetic friction force. If we look, this is a section where it's kinetic. These are applied forces. I want the friction force, which is the y-axis. So anywhere in the kinetic section, the friction force is going to be 10. So my force of friction for kinetic is 10. Still divide over, and you get, I think it's like 0.3 something. Yeah, 0.34. We're going to use the table above to decide what materials we're looking at. If it has a static coefficient of 0.85 and a kinetic coefficient of 0.34, static 0.85, kinetic 0.34, that must be cardboard on carpet. The largest momentum is mass times velocity, so let's just find it. 40 times 10 is 400. 55 times 7 is 385. If it's at rest, that's a velocity of 0, so 0 momentum. This one has a momentum of 300, so the one that has the largest momentum is A. Which card, ignore that part, that was a typo, would experience the greatest change in momentum? So change in momentum is m delta v. Obviously, we don't have m delta v, but we also know it's equal to the f delta t side. So what I can do is, if I have force and time, I can multiply. That's my impulse, but that's also my change in momentum. So this has an impulse of 0.5. This has an impulse of 1. This has an impulse of 0.5. That has an impulse of 0.5. So the one that has the greatest is B. 13 or 12, we've got a 3 kilogram steel block. It's at rest on a frictionless surface. And a 1 kilogram lump of clay is propelled horizontally at 6. So 1 coming in at 6, 3 at rest. Upon collision, they stick together. So the 1 and the 3 now stick together and move to the right with the speed of what? So we're going to plug into our m1v1 plus m2v2 equation. So 1 times v plus 3 times 0 equals 1v plus 3v. Here, my total momentum before is just on this side, right? This is 0, so it's a total momentum of 6. These two, 1v and 3v, have to add up to 4v, and they also have a total momentum of 6, so divide over, you get a velocity of 1.5. And we knew it had to be slower than 6 because you just picked up extra mass. This one has to give away some of its momentum to give this guy momentum, so of course it should have been less than 6. That's reasonable. So, similar setup. Upon collision, they stick together. How does the momentum of the clay before compare to the momentum of the clay and steel after? So think about it. This one has a momentum of 0. This has a momentum of, I don't know, let's call it P total, because whatever the momentum is here is the total momentum if this one is 0. Now when they stick together, these two together must have the same total momentum. So they have a total momentum of P total, which is why C is your answer. The momentum of the two of them together is just equal to the clay before, because this one is 0. The clay's momentum before was the total momentum, so it's the total momentum after, because total momentum is conserved. The type of collision, so when they stick together, that is an inelastic collision, and it's because they stick together. The clay, does it gain or lose momentum? So when the clay hits this guy, it's going to slow down, which means it's going to lose momentum. I'm going to say because it slows. The steel is going to gain momentum because it gets faster, right? It wasn't moving and now it is to the right, so it just gains some momentum. What do we know about the amount of momentum that the clay lost compared to the amount of momentum that the steel gained? So let's think about it. I don't know the numbers, but let's say this guy lost 2 units of momentum. If the clay lost 2 units of momentum, that didn't just disappear. That means that the steel gained 2 units of momentum. So however much the clay lost is equal, so the amount clay loses is equal to the amount that the steel gains, because total momentum is conserved. So you can think about that in terms of like the money examples I was using, right? If I have $10 and you have $0 and I give away $3, I lost $3, you gained $3. You can't have gained 4 if I only lost 5, and I can't have lost 3 and you only gained 2, because where did that money go? Same with momentum. That total momentum has to stay the same. What do we know about the impulse that the clay experiences compared to the impulse the steel experiences? So impulse is F delta T, and it's also change in momentum. Well, we just said that how much the clay changed is equal to how much the momentum of the steel changed, so they must have equal impulses. You also can think about it as F delta T. When they hit, they're experiencing the same force, right? Equal and opposite, and they're experiencing it for the same amount of time because the clay can't hit the block longer than the block kicks back. So then they would have the same F and T, which is the same impulse. Either way, you get the impulse is the same. Michelle throws an eraser up into the air at a velocity of 6.5, so that is my initial velocity. When you're talking about something moving through the air, you know the acceleration is just the acceleration due to gravity, negative 9.8. And we know we're talking about the maximum height. At the very, very top, your velocity is going to go to 0 before it turns around and comes back down, right? If it's positive at first and then it's going to turn around and become negative, it has to pass through 0 for a second. So now we're looking for how long it takes, which means I'm looking for time. So I'm going to use the VF equals VI plus AT equation. So 6.5 plus negative 9.8 T, 0. I'm going to subtract the 6.5 over. Now I'm going to divide the 9.8 over. That gives me a time of things like 0.66 seconds. All right, B is asking for the actual maximum height. Now I'm looking for the distance traveled. You can use either equation now because you have everything except for distance. I plugged into the D equals VIT plus 1/2 AT squared. Initial velocity is 6.5. Time was 0.66. 1/2. Acceleration is negative 9.8, and it's still the same time, 0.66 seconds. Squared, and now I think it's like 2 point something. Let's check. So that, yep, is 2.16 meters is your distance. All right, we've got a mass of 2.5. I want to find weight. Weight is just asking for Fg. Fg is mass times 9.8, so we're just going to use 2.5 times 9.8. That gives us 24.5 is our Fg. I want to know what's the magnitude of the force that must be applied to keep the box moving at a constant velocity. So as soon as you see constant velocity, you know your forces are balanced. So I've got my Fg is 24.5. That means my normal force is also 24.5. I want to know what the applied force would have to be. So F applied is my unknown, but it's at a constant velocity. So constant velocity just means that this is going to be equal to this one. Now I need a force to keep it at constant velocity because there is friction. If it's moving, right, keep it moving, then it's already moving, which means we're talking about kinetic friction. and we're looking at rubber on concrete, so that's a coefficient of 0.8. So force of friction is mu Fn. Mu in this case is 0.8, and the normal force is what we just found, 24.5. So that gives me a force of friction of 19.6. And if the kinetic friction is 19.6, then to keep it at a constant velocity, I need exactly 19.6 newtons. If the box was not moving at a constant velocity, but instead was pulled with a force of 25, so now my applied force is 25, and I still have the same Fg and Fn, what would the acceleration be? So to find acceleration, I'm going to use F net equals ma. I know my mass, I'm looking for acceleration, I just need to know what my net force is. Think about, my applied force is 25, but that's not my net force because I still do have friction, right? The friction, if it's not at a constant velocity, but I'm pulled more, it's obviously still moving, it's just going to accelerate. I still have a friction force, and it's still the kinetic friction. It's the same kinetic friction as before. All I did was, instead of being enough to balance, I now have more so that it accelerates. To find the net force, write 25 to the right, 19.6 to the left. I'm just going to subtract those two, which is 4.9, equals mass of 2.5 acceleration. And then now we're going to divide that mass over, and that gives me an acceleration of, is that the acceleration? 25 minus 19.6. Oh, my bad, that's 5.4. All right, and then divide the 2.5 over, and that gives you an acceleration of 2.16. Okay. All right, Jonathan is holding his physics book and goes ice skating, but he doesn't know how to skate. He pushes off the side of the rink and is slowly moving away at a speed of this. So if this is the rink, here's Jonathan holding his physics book and moving in the negative direction at a speed of 0.2. I want to know what's the total momentum of him and his book as he moves away. So momentum is just mv. Total momentum, I want to include both masses. That's 250 and 10. So that's a total mass of 260. And the velocity, they've already been given, is negative 0.2. Right? So this total mass times the velocity gives me the total momentum. And the total momentum is negative 52. 260 times 0.2? Yeah. Alright, so this is how much momentum I have. It's kilograms meters per second, because I multiplied kilograms times meters per second. How far away will he be after 10 seconds? So t equals 10. I know the velocity is negative 0.2, and I'm looking for distance. This isn't accelerating, right? He's just moving at this constant velocity, so I can use the v equals d over t equation. Velocity is negative 0.2. Distance, I don't know. The time is 10. Multiply this up to get distance by itself, so that gives me a distance of negative 2, negative 2 meters. So he's going pretty slow, so after 10 seconds he'll just be 2 meters away, and in the negative direction because the velocity was negative. Now suppose he wants to get back over here, right? He wants to go this way, but he doesn't know how to skate, so he's going to use his physics book to get back to where he, oh my god, this is so dumb, to get back to where he's going, where he started, right here. So if he's moving to the left and he wants to go to the right, we're going to use conservation of momentum. So if he throws the book really, really fast, right, if he throws it this way, then he will go the other way because it'll still have the same total momentum. I need to have a total momentum of negative 52 to the, in the negative direction. If I throw the book fast enough, then he will have to go the other way to compensate to keep the same total momentum. So, Jonathan can throw his book. So think about the direction he needs to throw it. He needs to throw it super fast in the negative direction so that he will go the opposite way. So he can throw his book away from the side so that he will move towards the side. And we need to explain why this is happening. This has to do with conservation of momentum. So the total momentum of him and the book must still be negative 52. So your total momentum has to stay the same. So if he throws the book fast enough, in the negative direction, or you could say the y direction, in the negative direction, he will have to move in the positive direction for total momentum to be conserved. Alright, how fast did he actually need to throw it in order for him to move towards the ball? This is a positive direction at point 2. So I'm going to draw the before and after picture because I think that's going to help. You've got the 250 and the 10. At first, they're both moving negative point 2. Now, afterwards, you're looking for what velocity do you need to throw the book at in order for Jonathan, the 250, to go in the positive direction at point 2. So now we're just plugging into our m1v1, m2v2 equation. So you've got 10 times negative 0.2 plus 250 times negative 0.2. That's the before. And the after is 10, I'm looking for its velocity, plus 250 times positive 0.2. On the left side, we should be getting negative 52, because that's what we said we would be getting. That's the total momentum. Did I get that? Oh yeah. Negative 52 equals, this is 10v, 250 times, I think that's 5. Nope, 50. Plus 50. Now I'm going to subtract the 50 over. Negative 52 minus 50 is going to give me negative 102 equals 10v. Now we're going to get the v by itself by dividing by 10, so that gives me a velocity of negative 10.2 meters per second. Now the question is, if he only wants to go back at point 2, why does he need to throw this decimal point? Why does he need to throw the throw the book with so much velocity? Why does he have to throw it so fast? And it has to do with his masses, right? So he has a much greater mass, the book has a much smaller mass, so in order for him to get enough momentum to go back at point 2, the book with its smaller mass would have to be going much faster. So he needs to throw the book so fast because the book has much less mass than him, so needs to go much faster than 0.2 to get him to move at 0.2 meters per second. Right? Because you need their momentums to cancel out, not their velocities, or to balance out, I guess. Not their velocities, so a much smaller mass needs a much greater velocity than the greater mass, which will have a smaller velocity.